Lecture 9, Pipes and Shared Memory. In addition to the message passing mechanisms we've seen so far, signals and network, we can also use pipes and shared memory. Pipe is actually a good transitional topic between message passing and shared memory because it has some aspects of each, and therefore it's the one we will talk about next. Okay, UNIX pipes are a mechanism of communication, tempting as though it may be to think of pipes as a method of transport for a certain plumber who likes to jump. Now, you create a pipe to establish communication from one process to another, usually between a producer and a consumer, because pipes are unidirectional. The producer writes in one end, and the consumer receives the data that was put into the pipe on the other end. If bidirectional communication is desired, you need two pipes, and they are set up so they go in different directions. And the UNIX method for creating a pipe is called pipe. That's not surprising. The one for socket is called socket. The one for opening a file is called open. The good names were not taken. Pipe takes one argument, and it is an integer array of file descriptors, and that array is of size 2. File descriptors at index 0 will be the read end of the pipe, and file descriptors at index 1 is the write end of the pipe. And yes, this does mean that the pipe is thought of as a file, but you know already that Unix thinks it's a everything is a file. A pipe is in memory, but it doesn't matter. We'll interact with it as though it is a file. So a pipe would look something like this. When we have a pipe that is being shared between a parent and the child, we have our file descriptors 0 and file descriptors 1, referring to the ends of the pipe, and the parent and the child each incidentally have each of those. We'll have to choose who does the talking and who does the listening. If your parents are strict parents, then you know it is the parent that does the talking and the child that does the listening. But in any case, it's our decision of how it's implemented in our program. Now, the actual implementation of a pipe, it is a block of main memory, and it is treated as though it is a circular queue. Every entry in the queue is fixed in size, and it's usually one character at a time. The sender can place a message into the queue in little chunks. The receiver tends to get data one character at a time. These can be aggregated when you use the read and write commands, so you don't have to manually add every single character in a for loop, but in an implementation level, it operates on one character at a time. And as with some of the other communication mechanisms that we've talked about, the sender and the receiver need to know what is the length of the message. And again, just like we talked about with the network, you have some choices. One is you can have a declared length at the start, in which the sender says, I'm going to send you a message, and that message is 288 characters long. Yes, great. Then you know when you've received all 288 characters, you're done. Alternatively, you have some sort of termination character, or alternatively, I suppose, to that, you could even close the pipe. Either way, you need a way of indicating that we are done, and either a predetermined length, a declared length, or just closing when we are finished means that everything is going to work as expected. And it is allowed to store a UNIX pipe on disk. When that happens, it is referred to as a named pipe. You're effectively saving the file, although it isn't really a file as much as it is a buffer. Unless you make a pipe a named pipe, it really only exists as long as the processes are communicating. And a regular pipe has to have a parent-child relationship. Why? Otherwise, they don't know about each other, the sender and receiver ends, and it will only work if you actually have this relationship. A named pipe does not, because you can, of course, refer to the pipe by its name, and should you do so, then it doesn't matter if the parent and child relationship exists, because processes that are unrelated can just access the pipe by referring to it by name. And a named pipe can be used in either direction, but it has to be only one direction at a time. Only one person can talk concurrently. You might have worked with a pipe using a command line. You can use this to redirect output from one command as the input for another. A command like cat fork.c and then the pipe character to less creates a pipe of sorts. It takes the output of the cat program and delivers it as input to less. This is helpful when you have a process that produces something on standard out, and then you can send it to the next thing as standard in. That's quite convenient. So it takes the output, cat just dumps the contents of a file to standard out, and redirecting it to less means it is redirected into an editor or reader that allows for scrolling and paging through that data. The example that's in the slides as well as the notes is the same as the one that we are looking at here. This one just allows us to actually play around a little bit and see what's going on. So, as is typical, we have our include directives at the top of the file, and we have some define directives as well. And buffer size here is defined to be 10. You could really make it anything you wanted, but for the purposes of the example, we have made it 10. And there are also define directives that say read end is 0 and write end is 1. This matches, of course, what we discussed earlier when we were talking about how does the pipe work, and that it uses the file descriptors, and file descriptors at index 0 is the read end, and file descriptors at index 1 is the write end. But rather than just having explicit values of 0 and 1 somewhere in your program, making it less legible, making it harder to remember, is this the read end or is it the write end? This is a use of a define directive that can help with that. And you might have heard, just general guidance about define directives being evil, and they're a tool. Like anything else, they can be used for evil, but you can also use them for good, and this, I would at least argue, is an example of using it for good. Okay, so we're going to define two character arrays, one for write message. It contains the word greetings, and we have a read message, which is also of buffer size, and then we will define our file descriptors, and file descriptors is an int array, and the int array is of size exactly 2, and finally there is a PID type, because as you might imagine we're going to use fork in this example. Okay, so we call on line 18 pipe with file descriptors, but we didn't actually assign the file descriptors any values. They just contain stack allocated garbage. That's okay. The file descriptors are initialized by the call to pipe on line 18, and therefore this is working as intended. They don't have meaningful values before they are initialized, and they are initialized by pipe. Setting them to 0 doesn't serve any purpose, although you could if you just thought it was good habit. However, they're overwritten by the call to pipe. Pipe could, in principle, fail. If that does happen, then we return -1 and exit this program immediately. On line 22, there is a printf statement here. This is left over from a previous term in which a student asked, well, what are the file descriptor numbers if they're just integers? What do they look like? And I'll leave it for you for the moment to think about, what do you think they are? When we run this program, you'll see what they are, but for the moment, just think about what they might be. Okay, at line 24, we fork, and therefore a child process is created. We're going to check and see, did the fork succeed? If not, exit. And if the process ID is greater than 0, this is the parent process, and the parent will close the read end file descriptor, write data, write the message to the destination, and then close the write end when it's done. The child process closes the write end because the child is only going to read. It will read from the read end, and it will print out whatever thing it observed, and then close the read end. Now, we intentionally, both as the parent and the child, close the end of the pipe immediately that we are not going to use. There's no crime in delaying that a little bit. You could put the close statements together if you wanted, but it is polite to release resources as soon as you know that you are finished with them. And if it is a unidirectional pipe and we are doing the writing, we know we're not going to use the read end, so we should close it right away. and not risk forgetting it or not risk delaying it unnecessarily. So that is why that happens immediately. Again, as you can see, we should expect that read is a blocking call on line 38. So we do have, again, a measure of coordination here because, well, when we want to write the data, we can write the data into the pipe. If we want to read some data, if there isn't any data to read yet, well, we'll just wait until there is some. And therefore, we won't go on to the statement here, printf read of whatever it was, unless we actually received some data that we can use. So that provides us with all the coordination we need. We don't have to use wait, although in principle you could. Well, it doesn't work as well in this scenario as in some other scenarios because it's the child process that's actually got to wait for the parent. Okay, so we'll run this. Let's see how we do. Okay, two things. Number one, the file descriptors are 3 and 4. 3 and 4. You would probably have imagined that file numbers corresponding to the pipes are quite large. The answer to that is no. We will see in a later discussion about how files work in some more detail and concurrency in file systems that these numbers 3 and 4 are just the table entries corresponding to whatever files are open in this process. And so when we create the pipe, that opens 2 new file descriptors, and they're assigned 3 and 4 because 1 and 2 and 0 are already taken. And therefore, we just assign them whatever the next available numbers are, and those are the entries in what is effectively an array of open files belonging to this process. So that's a neat little detail. It's one of those things where it might be a little unexpected. Okay, the other thing worth noting is that we read a message of greetings followed by the @ symbol. Why is there an @ symbol? Let's open up the code again. There was no @ symbol in the original message. Okay. What happened here? The printf routine, when it prints something like this here at line 39, it continues going until it gets to a 0 byte somewhere. We're supposed to put the null terminator where it belongs, and in this case, I'm not sure that we did. We read some data from the pipe, but we read it into this read message character array. The read message character array was never initialized, and we're not certain that the buffer contained zeros because it contained garbage, and we're not certain that what we read out of the pipe also contained a null terminator. Because evidently it didn't. So what we could do to address that is, of course, initialize it. We could memset read message, set it to 0, and make it buffer size. That will initialize all of the bytes to 0. Therefore, if we read out of the pipe some data, but it doesn't fill up the entire buffer, that's fine. All the remaining bytes that were not overwritten by the read will just be 0. That's fine too. One of the other things that you could do, and I'll compile this and run it just so you can see that it works before I discuss the other strategy, is, well, now it works as expected. But if I delete the memset, one of the other things you could do, and you'll see this sometimes as well, is you will just manually assign the last index to be 0. In which case, after we've done the read, we will do something like this. Read message at index buffer size -1 is assigned, and then the explicit 0 null terminator. It has a little backslash in front of it, and that means the last position here will be assigned 0. Let's try that. That also worked. However, it's not as flexible as the memset one because we're not sure exactly how many bytes we read. The actually correct thing to do in this case would be to check how many bytes we've read. The next thing that we could do as well is we could say, well, when we did write, we wrote using string length, and I said, well, string length doesn't count the null terminator, so what if I added a +1 here to actually make it write that null terminator? Does that solve the problem? And the answer to that is also yes. So it's really a question of what we were expecting versus what did we send. Sometimes you don't want to send the null terminator, and sometimes you do, but it is important, however you deal with it, to make certain that your buffer, especially one that you're going to treat as a string, has a null terminator, because it's very easy to just go way off the end, and you will not be happy with the result because you will print some garbage and or possibly have a segmentation fault in your program. The last thing I want to mention on the subject of the pipe is that you can create a named pipe using the system call make FIFO, that is first in, first out, because that's sometimes what a named pipe is referred to as. And you just treat it like a regular file. It is manipulated with the usual system calls, open, read, write, close. The difference is that when you write to a file, you're writing to persistent storage. When you are writing to a pipe, that is a named pipe, it's just going into a memory buffer of some sort. On to shared memory. Now, shared memory is the last kind of interprocess communication that we want to talk about, the pipe is nice and all, but it's not super practical. Again, it requires a parent-child relationship, and it's not that different from working with the file system, but shared memory is quite good at certain things. Shared memory is very valuable in that it is the only kind of interprocess communication where we don't have to do a system call every time we want to read and write. We have to do some setup, we have to manage coordination on our own in a way that's not the case with, say, using a message queue or using the network, but it does have a performance benefit. It will be better if we manage it correctly than asking the operating system every single time you need to read or write some data. Anyway, conceptually, shared memory is straightforward. A particular region of memory is shared, all of whom may read and write to that location. And as you remember from the introduction, normally a region belongs to exactly one process, and if a second process attempts to mess with it, that is a problem. The operating system has to be notified. And hopefully you also remember this diagram as well, which I totally trashed as being a totally unrealistic textbook type diagram in which the world is perfect and all the blocks are perfectly sized and everything is wonderful, rainbows and unicorns. Okay, yeah, we know that. The real danger, of course, is that there is a possibility that one process overwrites another's changes, and we're going to have to, again, come back to the coordination topic a little bit later on. Okay, now to actually practically share a segment of memory, we are going to use a key. And the way that we use a key is exactly the same as the way that we used a key previously for message passing with a Unix message queue, in that we can use IPC private if we want to generate a guaranteed unique key that way, or with the file to key function as previously discussed in sys/ipc.h. If you don't recall, the f to key function takes a file and a project number, so a path to that file, the project number, and it uses that to generate a key. The workflow for shared memory relies on the following functions, and these functions are defined in the header sys//shm.h, and the workflow for using it requires you to create a new shared memory segment. The one for that is called shared memory get. You attach the shared memory segment, so you connect your program to that shared memory. Then you can use the shared memory as if it is regular and ordinary memory. Then when you are done with it, there is detach. And you detach from the shared memory automatically if your program exits. If it dies, there's a segmentation fault and it dies, then you automatically detach from shared memory. And when you are absolutely sure that you no longer need the shared memory segment at all, and it's done by one process only, use the shared memory control function to delete it. It is important to remember, and I'm going to highlight this more than once, and you'll probably get a number of emails from the lab instructor that touch on this subject, that a shared memory segment, once created, is persistent until it is explicitly destroyed. So you can create a shared memory segment, detach from it, and it hangs around, and another process can attach to it sometime later. This means that while you are developing and debugging a program that uses shared memory, if your program is crashing a lot, or you're terminating the debugger, or you're just having some difficulties in terms of correctness of your program, it is possible that you have lots of shared memory segments in use that aren't getting cleaned up. Shared memory is a limited resource on a Unix system, and it is possible to be unable to create more because all of the shared memory has been consumed. For that reason, in the labs, we give you a script that cleans up all of your shared memory segments, and there are also occasionally sweeps where lab staff clean out shared memory segments that are not in use. But I want to emphasize it is important to make sure that you are cleaning these things up. Otherwise, you are consuming a limited resource, and that is unpleasant and makes the experience much worse for your classmates. So let's drill into the details now about how to actually carry out the workflow that was just on the previous slide. So to create a shared memory segment, or just to get a reference to an existing one, we use shared memory get. The fact that it also covers attaching that it covers creation as well as getting an existing one is why it's called shared mem get as opposed to shared mem create. And it takes three parameters: the key, the size, and the flags. The first argument is a key, which is either returned by the f to k function, as we discussed earlier for the message queue, or you can just put in the constant IPC private. Size is how many bytes of memory are to be shared. So the size of the shared memory segment, that part is not surprising either. And the flags are the Unix permissions, and those look very much the same as they did for a message queue. The permissions are specified using, say, 600 for read and write by the owner only and no access for anybody else. And they can be combined, again, with the bitwise OR operator, just the single pipe, with IPC create. If no segment with the given key exists, create it, and IPC exclusive. If create was used, fail if the segment already exists. And you combine these with the permissions as before. The return value of the function is an integer ID of the shared memory segment, and that is, again, just very much the same as how it worked with a message queue. Given a key and some flags, we got an integer ID, and shared memory is the same, so if you're familiar with one, it's relatively easy to transition to the other. Now, when you did the shared memory get, all you got was the ID of a shared memory segment, but we haven't actually connected it to our program. We haven't said this process wants to start using this shared memory segment. And for that, there is the attach function, which is shared memory at, shmat, and it takes three parameters. The first, the ID, is what you got back from shared memory get. It tells you the ID for the shared memory segment that we are trying to attach. The second parameter is where you want it in memory space to go. In principle, as an advanced user, you could be very specific about where you want the shared memory to go, but I can't think of a good reason why you would do this. You should always use null. That says, operating system, you decide where it goes in memory. If you don't do that, your program might not work as expected on different machines, or even at different times, depending on what the state of memory is. So I would not do that. I would always use null for the address where it's going to be attached. As for the flag, the only thing that you could put there is the shared memory read-only flag. And if you do that, it really does attach the memory in shared-only mode, and this is enforced. If you attempt to write a value into shared memory, which you have attached in read-only mode, that results in a segmentation fault, and that isn't what you want usually, so yeah, that's bad. It might catch bad behavior, but you should not normally expect to encounter a segmentation fault. But I mean, how do you know what the segment ID is? Well, I mean, how do we know? Yeah, if we created the segment ourselves, we know where it is. Presumably, you want some other process to have it as well. So, I mean, you can use the file to key method, in which case you get the same result. So as long as everybody agrees we're going to use this file and this project number, that works. However, in a situation where you have a parent and child relationship, you can actually set up shared memory before the call to fork, in which case the child gets the shared memory segments attached as well, and it saves you from having to set certain things up. So that's kind of nice. Now, the return value from the attach call is a standard C pointer. It's a void star pointer with the address of shared memory, so it tells you, this is a pointer to the shared memory. Okay. If we're done with it, we can detach. And for that, we just call shared memory detach. It is very easy. It takes only one parameter, and it is whatever value that you were provided by the call to the attach function. And if you forget, as I said, this happens automatically when your process terminates for whatever reason. But don't forget, you shouldn't forget. It's rude to forget. If we're certain that a shared memory segment is no longer needed, then we can use the deletion routine, and it is shared memory control. Again, like the message queue management function, it can do a lot of things. The only one we're interested in right now is the ability to delete it. And given a shared memory ID, and the argument IPC remove, IPC RMID, or remove ID, however you want to pronounce that, and you leave the last argument, the buff here, as null, that sets up the shared memory segment for deletion. But deletion might be deferred. And by deferred, I mean it doesn't necessarily happen immediately. As long as that memory is attached somewhere, it won't be deleted. It's been scheduled for deletion. It will eventually be deleted, but that only happens when the last attachment to it ends. If you want to think of it like a file, it is like a file in Unix, where if a file is open, the file won't actually go away until the last process closes it. In Linux, incidentally, it is possible to attach to a still existing segment if it has been marked for deletion, but that's actually not consistent behavior across Unix systems, and you shouldn't count on that. This is unreliable and not portable. So let's go to a shared memory example. This one is a minimal shared memory working example where we are going to transfer some data from one process to another, and they have this parent and child relationship. Okay, so we will define the shared memory ID here up at the top of main, and we will do it with shared memory get. It will be 32 bytes in size. We will then get it, and it returns a shared memory ID, and it's a newly created one with permissions 666. Doing this before the fork means there's no requirement to communicate to the child process or to the parent process what the shared memory ID is, because it's already been known to both of them at the time of fork. So the parent process will just wait for the child to run as the first thing that happens after fork. So we'll skip down to the child and talk about its code first. So the child process will attach to the shared memory segment that has been specified, and it will use null, allowing the kernel to decide where is it going to be attached in main memory. We will then memset it to 0 because we're going to write a string in it, and then we will print f in there. We will set the text to read hello world, and then we will detach the segment as the child, and the child will exit. The parent process will then wake up. It will then attach the shared memory segment. It will then read whatever was in shared memory, and it will just interpret it as a character and detach the segment, and then schedule it for deletion before exiting. Small as this example is, it shows us a number of different things that are noteworthy about what happens when we use shared memory. For one thing, there is a period of time where the shared memory segment exists, but no one is attached to it. One of them is after the shared memory get call has been created, but before fork. Shared memory segment has been created, but nobody is attached to it right now. And then the child process attaches to it while the parent is waiting, and the child process detaches. And at that point, once again, there is no process currently attached to the shared memory segment, but its contents remain. It doesn't go away, it hasn't become invalid or anything like that. It's still waiting for when the parent process wakes up and attaches to it at its first opportunity. The other thing that we see is that once we have attached the shared memory segment, we treat it just as though it is regular memory. We called memset in the child on the memory immediately, and we used it as a target for sprintf. The parent process decides it's just going to interpret the shared memory as though it is a character pointer, as opposed to just a void pointer, an untyped pointer. And it's treated as though it is regular ordinary memory, and there's no special steps that we have to take. We don't have to invoke the kernel to do a read or a write. We just read and assign variables as though it is any other memory. Now, the coordination thing is solved here by the use of wait. We know already that coordination is a big problem when we are dealing with multiple processes, but at least using a way that we have already learned, we can make sure that we are doing things in the correct order. The child process runs and sets the value before the parent process runs and attempts to read the value. The other thing that is kind of noteworthy about this, the shared memory is just a blob. It's just a block of shared memory. It happens to be 32 bytes because that's what we asked for, but it doesn't inherently have any structure. And we've decided we're just going to treat it like a string, and we can get away with that because, of course, hey, you can do whatever you want. This is C. You can say pretend it's a string, and yes, it's a string. I agree, the compiler says. But if you are actually interested in storing some more data in memory, perhaps more than one thing in shared memory, you can impose a structure of some sort by saying, actually, I want you to treat it as though it is struct widget, and then you know how to assign fields and set fields and what have you in the widget, just like it's a regular variable. Similarly, if it's an array, you can treat it like an array. That's fine as well. You could, if you want, split up your things that are to be shared into different shared memory segments. And I know from looking at what some people do on labs that sometimes they take this approach in that they have one shared memory segment that represents all the things of type X, so it's an array of type X, and they have another shared memory segment that's an array of type Y, and so on and so on. You don't have to. You could have just one very large shared memory segment if you wanted, as long as you know how to structure it. When you're talking about variable numbers of things, that might make it hard, but it's really all the same as far as the operating system is concerned. Now, someone asked about this after the first offering of this course, so I felt a need to add a little note here to perhaps allay some fears that you might have. You might have a small security concern, which is that does anybody who knows the key or the ID have the ability to attach to my shared memory? In principle, you could just create a for loop that tries to attach to all memory everywhere and see what you can find. The answer to that is no. If it is a process run by a user J999do, that process can only attach to memory that's shared by another process run by that user, permissions allowed. The owner can reassign ownership with the shared memory control call, but as I've said, we're not going to do anything with that other than the ability to just destroy a segment when we're done with it. And so there's no concern about leaving your memory unattended and it being nicked by anybody else. With that in mind, please do not leave your memory unattended. I reiterate that you should be sure to destroy your shared memory segments when you no longer need them, because they are a limited resource and it is possible for the server to run out. There's one more kind of shared memory that I want to talk about, and it is consult the map. I like these old maps in which there's a fair amount of uncertainty about what is the geography of certain countries. Like, is California attached to anything? I don't know. We would have to send people to sail over there, and that's far away, and we're not good at that yet. So yeah, consult the map. Actually, the memory map. Okay. Memory map is actually nominally intended to map a file into memory. You can use this for interprocess communication if you want, but it is actually also intended, like I say, for just having a file appear as though it is memory. When we fetch data from a buffer, that might be conceptually a little easier and more straightforward than when we do a read and a write. And mmap says, actually, I want you to treat this file as though it is memory, thus allowing us to just iterate over things kind of conveniently. So if you want to map a file, you have to use the function mmap and do the following things. It takes the following arguments. It takes an address where you want the mapped region to go. As with attaching a shared memory segment, use null. You should let the system choose, unless you have a very good reason why you need it to go in a specific place, but you shouldn't. The second argument, length, is how many bytes we want to map. The third is the protection flags, your read, write, and execute stuff that applies. It's not quite the same as the UNIX permissions, as we're going to see. The mode is how a flag is used for the mode for how we're going to map it. We'll have to come back to that one, as it requires some explanation. FD is the file descriptor of the file that we want to map, so which file it is. And offset is how far from the start of the file that mapping actually begins. So you don't have to start at the beginning if you don't want. So the protection flags could be the following things. They could be none, they could be read, write, or execute, and they can be combined with a bitwise or operator. That is required to be consistent with how you chose to open the file using the open system call. So if you said, I want to open the file read only, you can't then set the protection flags to allow both reading and writing, because that's inconsistent with what you did with open. If you said you wanted to open the file for reading and writing, then it would be okay to enable those things. The protection none operation, incidentally, forbids all access to that file. Any attempt to read or write that memory produces a segmentation fault. And you might be thinking, who would ever want this? As the sign says, alles verboten, everything forbidden. What's the point of it? Well, if you want to, you can put guards at the start and the end of a region of memory. And that means if a process accidentally goes out of bounds, you accidentally write off the end of the array, or you go before the beginning of the array, it generates a segmentation fault and it enforces the rules and tells you immediately of the error. As we know, by default, that is not the behavior in C. C will gladly let you write off the end of an array, unless you're very unlucky, and it just happens to cause a crash. And therefore, you can, if you have something mmapped, choose to enforce this protection none, and therefore make sure that there is an area where any access causes a crash right away. Flags have two options. There's private and there's shared. Private means that modifications are not visible to other processes that are mapping the same file, and they're not written out to the file that's on disk, referred to as the underlying file. That means that we loaded a copy of it, and it's just our copy. We can play around with it, but it doesn't get saved. If we choose shared, modifications are visible to other processes, and they will be written out to the file, but maybe not instantly. The system might choose to delay writes out to the file, basically for performance reasons. That if it tried to update the file on disk every time you changed 1 byte, that would be very slow because disks are slow and updating it every single byte is kind of inefficient. It would prefer to wait and actually update a chunk at a time. That might not be what you want. If you want the results or the changes to be visible immediately, there is a function that we can use that will more or less make sure that everybody agrees on what we're going to do. As you might imagine, the private flag is what makes sense if we just want to work with a file ourselves and have it as our little scratch space. And shared is what we're going to use when we want an interprocess communication type scenario. And this diagram here shows you a memory mapped file, and basically what we expect is that we have some amount of data in our memory shown here on the left, and then the memory map portion of the file really means this is the file that is on disk, and it was created with some offset. And when we do a read or write on an address that is within the arrow marked by len on the left side there, it actually ends up getting flushed out to disk. And changes become visible, assuming we mapped it in shared mode. If you want to change the protection rules for a section, there is mprotect. That does actually sound like the name of some startup company now that I think of it, and I suppose if I Googled it, I might find that there is such a thing. But mprotect is used to set the protection rules, and you can use that to set the new rules for just a part of the segment. So from a certain address, set this length to follow these protection rules. Yes, the slide says port on the bottom. That's an autocorrect if ever I saw one, and it should be prot to match the mprotect definition up above. And then there is Synchronize, msync, not the 90s music group. Now, this takes 3 arguments, takes an address, takes a length, and takes flags. So address is what memory do we want to synchronize, length is how many bytes, and flags are the mode for synchronization. So this is how we would trigger a write to disk. As I mentioned, for performance reasons, a change might not be written to disk right away. If you want that to happen, msync says, I actually want this to take place. I want it to be written out to disk. For flags, use mssync. That is blocking. There are more advanced options, of course, but we're not going to talk about them in the context of this lecture. And if we're going to use msync, it's probably that we want other processes to be able to see our change, and making it blocking makes the most sense. And finally, when we're done with a segment, we use unmap, and, well, the function for that is munmap, and you can unmap this particular address and then a length. So you can also do a partial unmap if you're so inclined. A segment is also unmapped automatically when a file is closed, when a process exits. It is, however, polite to unmap it when you know that you no longer need it. And to close out the mmap thing, we'll look at a brief example. This example will allow us to overwrite the contents of example.txt such that it contains a new message. It is now overwritten in a child process, and the parent will then see the updated message. It also gives a quick example of how to use mmap and then unmap and all that sort of stuff. There are a couple things we have to do. We have to add a define x open source. This makes GCC somewhat happier with our actual program. And there are some functions we need to include, including the function control. I knew I was going to do it, including file control and the memory management one here, mn.h. Anyway, we'll open a file. fd is open example.txt, and it is open in read-write mode. One of the things that we can do is get the size of a file. We didn't cover this in the file system lecture, but this structure called stat is how we can actually find out what is the size of a file. Stat tells us about some attributes of that file. And so struct stat st is declared here, and we will stat using the stat system call the file name, and it updates the struct that we have provided, and then we can ask, based on the attributes that we have just received, what its size is. That allows us to, in this case, do the mmap, and we will mmap, calling it with null, saying kernel, please choose where this is supposed to go, the size of the file, and we will open it in read-write only, and it's going to be shared using the file descriptor that we have opened previously on line 14, and then we'll take 0 for our last argument, because we want to start at the start of the file, so an offset of 0 makes sense. Then we will fork. The parent process in this case will wait for the child, and when it's finished waiting for the child, it will then print the new contents of the file, and then unmap the shared memory segment. The child process will erase what's in that file, write a new string to it. It says it is now overwritten, and then it will msync to force the data to be written out to the file, and then the child process will unmap it. You'll notice this program has one map and two unmaps. That is, of course, because fork. At the time when mmap is called, the parent process has created the memory mapped segment, and because the child process is an exact duplicate of the parent, when it is created, it also has this memory mapped segment, and therefore each of them separately need to unmap this. Okay, so if there's no further dispute about what this is supposed to do, then we can actually look at the example.txt. So you can see it says here, this is sample text. And we will compile our code, and then we can run it. And sure enough, the parent process reports that the new content of the file is it is now overwritten, and if we actually look at the file example.txt, that is the case. That's what happened. Okay. Is that the desired behavior? Sure it is. The child process was supposed to overwrite it, and the new content of the file is printed. This, like shared memory, created with shared memory get and attach and all that, has the same benefit of once we've mapped it into memory, whatever operations we want to do are just regular memory operations, so this printf statement doesn't require us to do a read or anything like that because we've mapped it and we can just treat it as though it is regular memory. Now, this example works acceptably. We successfully overwrite the data with new data, and the parent process sees the change, but weird things happen if we try to write less data than we were expecting. If we didn't do the mmap here on line 27, or the memset here on line 27, and then sprintf, strange things would happen. We would only overwrite part of the file, and then our file would contain some garbage. By that same token, if we wanted to write much more data than fits in that file, that wouldn't work either, because we can't just make the content of the file larger. In Linux, there does exist a remap function call, but it is not portable. It doesn't work on all systems. So using memory map for something like this, where we're trying to write a large amount of data out to a file or something, that doesn't work because ultimately we are limited by the fact that we can't just keep expanding the file as we would expect. With that in mind, there are certain situations where you might actually be okay with the result being the same size as the input. And a good example of that would be something like sorting an array. If we're thinking about a database could have lots of data stored in a file, and you could potentially want to sort that file. A sorting algorithm will produce, the file that's the same size, it contains the same data, it's just in a different order. So we can actually use a file for this purpose, and memory mapping that file might actually make it fairly straightforward to sort what is a fairly large amount of data. The sorted array is going to be the same size as the input, and this is something where we could potentially do some divide and conquer kind of thinking, share the work between different workers. And so when we come back to our next topic, we'll be entering into the next major part of the course, having finished our discussion of interprocess communication, and we will be thinking about threads and concurrency. And that will be the largest part, the largest unit of this course. So looking forward to seeing you in the next video.